A study on suspension testing development. Abstract: a suspension or shock is actually a mechanical tool made to scale back or wet surprise impulse, and deplete kinetic strength. The shock's duty could be to soak up or deplete electricity. Inside the car, it cuts down on the end result of journeying over rough floor, resulting in progressed nice ride, at the same time as increasing in comfort because of extensively decreased amplitude of disturbances. Passive absorbers are drawing for normal load conditions. This provides the best vibration performance of the standard load condition. However, if the increased weight is less than normal, it affects the strength and ability to hold the road. In order to achieve consistent lubrication performance from shock, it is important to change the durability and deterioration of its properties. In this article, a suspension test is introduced, consisting of 2 helical springs and a fluid damper. The density of the flux damper is adjusted to 4 different levels to achieve the flexible durability of the model type. The load from the vehicle will push the damper lower below its normal loaded height. Within this project, a surprise absorber was created in conjunction with a 3D model produced using Catia V5. Keywords: suspension design, experimentation, frequency, etc. Introduction. Passive fluid shock provides an easy and effective solution for comfort and handling of the vehicle. These convert vibration energy into heat by passing viscous fluid through restricted orifice and are widely utilized in car suspensions. Furthermore, the fluid dampers are often tuned by changing the fluid flow area to vary the vibration isolation performance. A shock damps the movement of both the sprung and unsprung masses of the car. The springs mass are that of the body and chassis of the car, and everything holding up by the springs. The unsprung mass consists of the entire module not supported by the springs. This includes the suspension system and every one module attached to it, the brake caliper, brake disc, wheel, tire and some of the suspension arms. Although there's a little amount of damping within the tire, approximately 2%, the suspension damper must do the bulk of the damping for this whole system. Meaning damping the sprung mass, unsprung mass and therefore the tire. While springs and sway bars produce force supported their displacement or deflection, dampers produce force supported how briskly you progress them, or their velocity. Therefore, the quantity of damping produced is proportional to velocity. This suggests the damper works sort of a dynamic spring. It produces force only it's moving. The first purpose of the damper on the car is to damp the sprung and unsprung masses at their resonant frequencies. For the sprung mass, this includes the pitch, heave and roll resonant frequencies. A secondary function is to regulate the speed of weight transfer throughout transients like braking, corner entry and acceleration. Within the best case, dampers. If everything else within the suspension drawing and component selection is correct, they simply damp the vibrations at resonant frequencies, control the speed of weight transfer and enhance vehicle comfort and performance. Within the worst case it dampens, they're asked to catch up on structural deficiencies, control heave, pitch, or roll imbalances, and catch up on drawing deficiencies like lack of suspension journey. 2 basic consideration for suspension. System. A suspension base. The suspension of requirements which ICS vehicles depend must upon satisfy different variety of operating conditions of the vehicle. These processes gives a dual purpose, contributing to the vehicle's handling and braking, permanently active safety and driving pleasure, and keeping vehicle occupants comfortable and fairly well isolated from road noise, bumps, and vibrations. The suspension also protects the vehicle itself and mounted systems from damage and wear. We will look into suspension calculation theory to have better look into drawing a better suspension system. B. Basic consideration. 1. Vertical loading. In vertical loading, road wheel comes across the bump on the road. It's subjected to normal forces, tensile or compressive, depending on the load irregularity, which are engrossed by the elastic compression, shear, bending, twisting properties of spring. To minimize the pitching effect of the car, the front system should have less spring action than the back suspension. 2. Rolling. Center of gravity of the vehicle is significantly above the bottom. As a result, while taking becomes the force acts upwards on the CG of auto, while the load resistance acts inwards at the wheels. This produced to a few turning the vehicle about the longitudinal axis called rolling. 3. Road holding. In road holding, the degree to which vehicle maintains the contact with the road surface in various types of directional changes, also as in line motion, is named as road holding. 4. Unsprung weight. Unsprung weight is that the weight of the vehicle module between suspension and road surface, rear axle assembly, steering knuckle, front axle, wheels. 5. Spring and dampers. Most suspensions use springs to absorb impacts and dampers, or shock absorbers, to control spring motions. Semi-active suspensions include devices such as air springs and switchable shock absorbers, various self-leveling solutions, as well as systems like hydropneumatic, hydromantic, and hydrogas suspensions. Conventional springs and dampers are referred to as passive suspensions. If the suspension is externally controlled, then it is a semi-active or active suspension. Mitsubishi developed the world's first production semi-active electronically controlled suspension in passenger cars. The system was first incorporated within the 1987 Galant model. A vehicle does not pitch when it goes over bumps within the ground, but instead moves up and down in parallel translation. It has a better springing balance. 6. Spring rate. The spring rate or stiffness is a component in setting the vehicle's ride height or its location in the suspension stroke. Vehicles which carry heavy loads will often have stiff springs to catch up on the extra weight that might otherwise collapse a vehicle to the bottom of its journey, stroke. Stiff springs are also used in performance applications when the suspension is constantly forced to the bottom of its stroke, causing a discount within the useful amount of suspension journey, which may also lead to harsh results. Riding in an empty truck used for carrying loads are often uncomfortable for passengers because of its high spring rate relative to the load of the vehicle. A system would even be described as having stiff springs and would also be uncomfortably bumpy. A luxury car, taxi, or passenger bus would be described as having soft and medium dampers. Vehicles with worn out or damaged springs ride lower to the bottom, which reduces the general amount of compression feasible to the suspension and increases the quantity of body lean. Sports vehicles can sometimes have spring rate requirements other than vehicle weight and load. 7. Mathematics of the spring rate. Spring rate is a ratio used to measure how resistant a spring is to being compressed or expanded throughout the spring's deflection. The magnitude of the spring force increases as deflection increases according to Hooke's law. Briefly, this can be stated as F equals Kx, 1, where F is the force the spring exerts, K is the spring rate of the spring. X is the displacement from equilibrium length, i.e., the length at which the spring is neither compressed nor stretched. Spring rate is confined to a narrow interval by the weight of the vehicle, the load the vehicle will carry, and to a lesser extent by suspension geometry and performance desires. Spring rates typically have units of N/mm. A nonlinear spring rate is one for which the relation between the spring's compression and the force exerted cannot be fitted adequately to a linear model. The spring rate of a coil spring may be calculated by a simple algebraic equation, or it may be measured in a spring testing machine. The spring constant K can be calculated as follows. K equals D4G / 8ND3, 2. Where D is the wire diameter, G is the spring's shear modulus, e.g., about 80 GPa for steel, and N is the number of wraps and D is the diameter of the coil. 8. Damping. Damping is the control of motion or oscillation, as seen with the use of hydraulic gates and valves in a vehicle's shock absorber. This may also vary, intentionally or unintentionally. Like spring rate, the optimal damping for comfort may be less than for control. Damping controls the journey speed and resistance of the vehicle's suspension. An undamped car will oscillate up and down. With proper damping levels, the car will settle back to a normal state in a minimal amount of time. Most damping in modern vehicles can be controlled by increasing or decreasing the resistance to fluid flow in the shock absorber. 9. Damping ratio. The damping ratio helps us establish which case of the damped motion we are considering. The table presented below will assist you interpret the results obtained from the damping ratio test. Note that the damping factor can't be negative. Table I damping table. There are 3 useful formulae used in our damping ratio calculator. We will present each of them with an explanation below. 3. Where C damping coefficient, in Ns/m, and Cc critical damping coefficient, in Ns/m. This is the most basic formula. If the damping coefficient is any less than the critical damping coefficient, the result will be less than 1 and imply that the system is underdamped, as expected. 4. Where m suspended mass, in kg, and k spring constant, as seen in Hooke's law, in N/m. This damping ratio formula is similar to the first one, but we used the fact that Cc equals 2V, mk. 5. Where 0.0 natural angular frequency. This is the magnitude of the angular velocity of the system when it undergoes the simple harmonic motion, in rad/s. In this case, we rearranged the formulae further, using 0.0 equals V, k/m. Notice that if the values of the other quantities are established, you also know how to find the damping coefficient. This method is much simpler and more approachable than the ones we mentioned in the first section. As you may have noticed in the first formula, the critical damping coefficient and the damping coefficient units are the same. It means that the damping ratio is dimensionless. 2 degree of freedom quarter car model for analysis of a passive suspension is shown in figure. Sprung mass, M1, represents chassis and vehicle body, whereas unsprung mass, M2, includes suspension and tire. Quarter car models have been used for numerical simulations to evaluate vibration, isolation performance of the presented system. Sprung mass acceleration is the criteria used to quantify vehicle comfort performance. Point 1 Lower sprung mass acceleration gives better comfort and vice versa. Steady state response of the sprung mass acceleration for harmonic displacement of the unsprung mass is given as follows. 6. Damping factor, dot, is given as follows. 7, where C is the damping coefficient, M1 is the sprung mass, Wn is the natural angular velocity, W is the angular velocity of unsprung mass excitation, Ks is the suspension sprung stiffness, R is the frequency ratio, W/Wn, and Ypk is the peak displacement of the unsprung mass. Equation 1 is rewritten to obtain to include the mass and the sprung mass acceleration, steady state response under harmonic excitations of amplitude Ypk, and can also be written as follows. 8, where F is the unsprung mass excitation frequency. Equation 3 implies that the acceleration will depend on the sprung mass in addition to the excitation frequency. Simulation has been performed with the quarter car model to evaluate the effect of change in the sprung mass on comfort. Input parameters used in the simulations are given in Table 2. Acceleration response for different values of sprung mass is plotted in figure. It can be observed from figure that the passive suspension gives better comfort for maximum sprung mass. However, as the sprung mass reduces, higher acceleration deteriorates vehicle comfort. Figure 2 Sprung mass acceleration for different values of sprung mass. 3 Experimentation. Vehicle suspension testing machines are generally configured as 2 or 4 rollers in a rigid frame. The wheels of the vehicle under test are placed between the rollers. For normal operation to test the suspension on a vehicle, the vehicle's wheels are spun under the power of the tester. The speed of the test vehicle is applied. A dynamometer then measures whether the retardation force present from the speeding effect of the test vehicle's wheels is adequate. Drawing of testing jig is performed on Catia V5 and manufactured with workshop tools. To make it easy and affordable to manufacture, mounting and chem was made in 3D printers. Complete view of the CAD model is shown in the following picture. A specifications. Driving motor torque, 896 N/cm. Motor voltage, 12 V. Motor rating, 80 watt. Motor type, planetary gearbox motor. Max RPM, 18. Damper length, 200 mm. Damper stroke, 50 mm. Damper type, coilover and air shock. Rail material aluminum. Chem material, nylon 66. B. Testing conditions. The following section outlines a portion of the test programmed. The test cases detailed in this report are shown in Table. Table 3 Testing conditions. Condition full load. 1 No shock absorbers yes. 2 New shock absorbers yes. For the 3 condition states of 1 No shock absorber. 2 A fully functional shock absorber, i.e. within specification, for the suspension being measured. At a load approximating full load, 500 N, on the damper, the test vehicle damper was spun up using the chem roller of the test rig. For the data presented in this report, the hydraulic valves of the test rig were set so that the final speed of the roller reached 50 revolutions per minute. This meant that, with 2 flats per revolution, the frequency of the forcing function from the flats of the roller was 12 Hz. This was at or above the highest axle hop frequency measured for this trailer and suspension. Other speeds were used and data recorded for these. The results of that analysis will be reported in future papers and at other For results, the signals from the load cells under the roller bearings were conditioned and filtered with a 25 Hz low-pass filter to remove noise. Time series and peak-to-peak values are shown in the following section. Time series of wheel force signals portions, and representative samples, of the time series of the wheel force signals for the 3 states of shock absorber health are shown in figure. Resonance occurred throughout the transients from starting the roller compared with the steady-state running dynamic forces. This may be seen in the starting transients for the worn and no shock absorber cases in the 0.5 to 1.0 s or so before the signal settled down to fairly even excursions. Figure 6 example of dynamic range, peak-to-peak value, of the wheel forces. The values of dynamic range1 for wheel forces with the three conditions of shock absorbent health is shown in table. These values were derived from the dynamic data shown in graphical form. Table 4 results. Condition at 500 and peak-to-peak value of difference compared. Static wheel loading wheel force, kg, 4 with new shock. Flats with 4 mm absorber case. Excitation. No shock absorbers 280 47.1. New shock absorbers 132.0. Acknowledgement. First and foremost, I would like to thank my guide Drive SP Deshmukh, Mechanical Engineering Department, for guiding me to accomplish this dissertation work. It was my privilege and pleasure to work under his able guidance. I am indeed grateful to him for providing helpful suggestion, from time to time. Due to his constant encouragement and inspiration I am able to present this dissertation. I am very much thankful to Dr. A.T. Pizay, Principal, Government College of Engineering, IJERT for providing all the necessary facilities to carry out my dissertation work. I express my deep gratitude to Dr. R.K. Srivastava, Head of Mechanical Engineering Department for his valuable guidance and constant encouragement. I am thankful to all teaching and non-teaching faculty members of Mechanical Engineering Department, GCE IJERT, for providing help me directly or indirectly for completing this dissertation work. Last but not the least, it would not have been possible for me to resume the prolonged work of project without support of my family members. Constant encouragement and support of my family made me possible to complete the work.